Hi, I'm Tim, and this is my class presentation. I want to start with a fun fact. Although I'm a mechanical engineering major, I actually wanted to do urban engineering, where I first joined Tandon. This is because in my hometown, Shanghai, congestion was a huge problem, and I thought NYU and GLASS would support me to travel around the world and see how city planners of the most populous cities have tried to solve this problem. However, this initial goal has slowly shifted as my GLASS and undergraduate research experiences gradually helped me to find my true interest, which is in robotics and health. My leadership experiences of leading self-drive and TAing for EG1004 taught me how to motivate others to work towards the shared goal, and also introduced me to the high barriers to robotics technology. My survey experience in Indonesia and Climate Week taught me the diversity of struggles around the world and the importance of active empathy. My academic experiences in DTU, Denmark, and various NYU labs have equipped me with the technical expertise to solve problems and also how to collaborate with people of diverse ideas and skills. Moving on, I've attended many professional conferences, symposiums, seminars through my 3 years in GLASS, including in the states of California, Georgia, Pennsylvania, Michigan, Boston, and abroad in China and Europe. These events expanded my network of scientific collaborators whose guidance made me decide to pursue a PhD in College Mellon University. Finally, my global experiences of Denmark study abroad and international internships at a material startup company fostered my cultural awareness and revealed to me the importance of accessible and socially compatible innovations. The most meaningful and memorable experience was a service trip to Bandung, Indonesia, where I met many lifelong friends. Together, we spent 3 days in a village homestay, serving and helping a nonprofit village school called Sekolah Multicard. The school was facing financial challenges during expansion, so we presented our recommendations to the owner that can help them with this process. However, much to our surprise, our capitalist and tech-focused suggestions, such as charging fees for visitors and construction advanced infrastructures, were not well received by the owners, as they clashed with the community-driven nonprofit philosophy that the local school owners followed by. I still vividly remember the school owner, Denny, and his closing remark. The standard of living in Sekolah Multicaro is low, and so is its people's standard of happiness. What's important is that people have found happiness in their simple ways of life. It is experiences like this one that has shaped my mission to introduce community-aware and accessible technology through my GLASS project, which is an affordable and wearable sensor for human motion monitoring. Measure human motions is important for elderly care, rehabilitation, and physical therapies, among some other applications. But it's really challenging for most sensors, including wearable ones that can attach to the human skin or clothing to detect those movements. This is because our movements are highly complex and involves a combination of bending, turning, and twisting motions that allows us to get around our daily lives. Aiming to solve this challenge, my GLASS project focused on developing a wearable sensor that can measure these complex movements while simultaneously embedded into the clothing and textiles we wear. And the better news is that it is all achieved through the readily available materials of commercial finishing lines and conductive sewing strands. Previous researchers have discovered that when we twist together fishing lines and conductive sewing threads really tightly, they will form a spring-like coil structure, which changes its electrical resistance under different shapes. Yet, these structures tend to be highly stiff, which means it takes a lot of force to stretch them, and can only measure stretching but not twisting motions. As a fact of that, they cannot measure movements such as the twisting of our wrists when we're drinking or when we're driving a car. My research innovated on the structure, physical modeling, and integration of such sensors so it can both measure stretching and torsion when embedded into textiles. Through a supercoil structure, as shown on the left, it's able to have lower stiffness than previously proposed designs while offering better performance. It can be seen from the graph on the right. The extension behavior is showing green, and its flatter curve indicates lower stiffness compared to the conventional design in blue, which has a steeper curve. The same structure also allows it to measure torsion or twisting motions, experiments have shown the high performance of such sensors, including accurate sensing of torsion on the high stretch and high resolution on the left, and fast response time on the right. During experiments, the sensor slowly twisted through positive and negative 360 degrees, and its resistance gradually and consistently varied even when the change in angle is small. On the right graph, we can see that readings quickly stabilize with an average stabilization time of 0.67 seconds, meaning it can be used in applications where the motion is rapidly changing. Further, when embedded into textile, it can reconstruct the complex movements of the wrist joint. In the graph, the top row shows various poses of the wrist. The middle row shows the shape of the sensor during these poses, and the bottom row shows the constructed shape of the sensor in the blue dots and the actual shape in the green dots. We can see that it has a high level of matching with actual movements and has a maximum error of only 11% under extreme motions. Finally, I have developed a physical model for this type of sensor that can be adapted to different design configurations and used in various applications that require different precision and strength. From the graphs, we can see that model prediction highly aligns with experimental results and can predict resistance under a mix of stretching and twisting motions. In the graph on the right, torsion is drawn on the horizontal axis, and stretch or extension in the sensor is drawn on the vertical axis. The model is able to predict changes in resistance as displayed in the color of the graph. So why is this project relevant to my class and to the wider communities? This project has been submitted to the top journal of Nature Scientific Reports for review, with low cost of only $2 per meter to make and a high sensing performance. This design has the potential to make human health monitoring more accessible and effective, which also ties to the grand challenge of advanced health informatics, the UN goal of good health and well-being, and finally, the Tandon research area of data science, robotics, and AI. I wish to end from a quote from Steve Jobs. You cannot connect the dots looking forward, you can only connect them looking backwards. I thank GLASS for helping me plant the forest of dots, which allowed me to connect a clear path in my undergraduate and future careers. Thank you.